is a finite morphism. So that has a technical definition in algebraic geometry, but if you like, you can just think of it as the pre-image of a point is a finite set. That'll do just fine. So if you're familiar with topology and covering spaces, then this is like it's like a covering space away from some branch locus, and that's how you should think of an alteration, I think. There exists an alteration, okay, and the alteration will be denoted phi1, maps from x1 onto the variety that we're given, which is x, and an open immersion. Okay. Which sends x1 into some projective variety. So I'll say that, so such that 1, this x1 bar is a projective variety. Think of it as like the Zariski closure of x1 if you want, that's fine. And is a regular scheme. Okay. And then secondly, so 2, the closed. So this is a point that was made by Hans last time. What I'm about to write is not technically a closed subset, but I'll just write the little bar over it, and then we can just kind of ignore it for now. So if you say like that's not a closed subset in general, you're right, and I will just say that I am actually recording this directly from the paper, so it's a bit odd that that's not a closed subset, but it shouldn't really matter for what I'm about to say. So so this is, you know, all together, and I'll just put the bar over this. I'll denote it with some other color to indicate that it's like parenthetical. Okay. Inside of, well, I'll say it this way, is a strict normal crossings divisor. Strict normal crossings divisor in x1 bar. So this is maybe a little scary for some people who were not seeing this the last time. So what this is really saying is that, you know, if you've got a variety, okay, you give me any variety over any field of your choice. You pick some closed subset inside the variety, right? And what you want to do is you want to make the variety smooth or non-singular or regular. If the field is perfect, then it doesn't matter which word I say there. And you want to pull back this closed subset into this nicer object so that the closed subset becomes what's called a strict normal crossings divisor. And what's a strict normal crossings divisor? Intuitively, it just means that a divisor has the property that every time there's a self-intersection, it looks like this. That's intuitively what it means. So this is a strict normal crossings divisor. Okay, there is a more technical definition, but it's just not worth it. You know, it's just going to be too much. So it's a strict normal crossings divisor, whereas something like this is not. So this is one piece, okay, and this guy is not a strict normal crossings divisor. Where in each case I'm thinking of the divisor as living inside of like the plane. And so these live inside of some surface or something like this. Okay, so that's what we saw last time. And the so maybe I should ask first, does anybody have any questions about any of the statements or the hypotheses or definitions or anything?
Yeah, well, I guess it is, they want to state the theorem as general as possible. What if X itself was already projective? Then this whole thing with this phi1 and so seems to be not necessary. Then I would assume if x is projective, then x1 is projective, and then x1 is equal x1 bar. Is that what's happening then?
Yeah, I think in this case, yeah, the alteration would just turn out to already be, like the open immersion would be the identity map in that case. Yeah.
Okay. All right. So it is just to make a very general statement. I did it this way. Okay. Okay.
Yeah, yeah, this is like Stack's project style statement.
Yeah. Right. Exactly. Yeah.
Exactly. It's as general as possible. But
Yeah.
yeah, the funny thing is that like the first thing we do to prove this is reduce to like a very special case, right? So we say like, oh, yeah, the theorem is about any variety and any field, but really you can actually assume that the variety is projective, it's normal. So you can take the normalization, which is some modification, which is an alteration, of course. And then you can even go as far as to say that the closed subset is a divisor and the field can be algebraically closed. So all these things just like become not an issue in like a second. So I'll write these things down because I just kind of said it quickly. So
well, you did that last time. I think you should not waste too much time there. We know that you can reduce it.
Okay. All right. So just very, I won't explain, but I'll just say we may assume, for those who didn't see it last time also, so we may assume X is projective, X is normal, K is K bar, so it's algebraically closed, and we can also assume that Z is a divisor. Right, so that much is true. Okay. Now, that makes everything a lot easier. And if you're curious about that, just ask me maybe afterward or something. It's kind of unbelievable. So now there's this lemma that we spent a lot of time on last time. And so I won't spend as much time on this time, but I will just state it again because it's very important. I would say that this is probably the most important statement, one of the most important statements in the entire argument. So suppose that the pair xz, okay, so this is the pair x with its divisor over k. Well, let me not say that because that's sort of silly. We don't need all of that, right? So let me just say that. Yeah, so I'll just say it this way. Let's get right to the point. There exists a modification. So what's a modification? It's a proper birational morphism. Okay, so in particular, it's an alteration. Right, so modifications are alterations. So like a blow up is an example, right? And so of course we can take blow ups and we don't do anything wrong, right? It's fine. But there exists a modification. Let's call it, calls it this. Right, and a morphism, which we'll call F, that goes from X prime to a projective space of one less dimension than X, of varieties. So everything here is a variety, satisfying some things. And this is pretty remarkable. Every statement here is like, is quite a bit actually. So I'll summarize the first thing by saying X prime is actually the blow up of X in, well, I'll just say a finite set for now. That's fine. So this X prime is actually pretty, well, not easy, but it's fairly straightforward to say what it is. All fibers of the morphism F are curves. Okay, so they're one-dimensional. And they're not empty, but that's like, okay, we know that. It's fine. The smooth locus of F is dense in every fiber. The smooth locus is defined using like multivariable calculus stuff, right? You just take affines and pull back and then check that the Jacobian matrix has the appropriate rank. So then, let me say it this way. So the morphism that we get by restricting F to the preimage Z by the modification, which maps from the preimage to the projective space is finite and étale. So it's like a cover over an open well, yeah, it's not said that it's, that's fine, over an open subscheme of this projective space. So the idea is that not only can we find a modification of X so that it maps, right, there's a morphism to a projective space of one less dimension, but we can even go further and make sure that the divisor that we brought along with us can be mapped like as a cover onto the projective space, right? So it'll cover the projective space. So we can say even more. Okay, and then finally, because X is normal, I think I realized for those who were wondering why this doesn't depend on the characteristic, the normality hypothesis I think has to do with the fact that what I'm about to say makes sense. In other words, I can do intersection theory. So if X is normal, then the regular local rings of well, all the divisors are such that they have like regular local ring structure, right? So it's regular in codimension 1, and then I can do intersection theory. I think that's really what this X is normal hypothesis is about. So because X is normal, at least one fiber of F is smooth, which is to say that if we restrict F to that point over that fiber, you have a smooth morphism. And actually, I don't know why he says it like this, because it might be nicer to just tell the reader, like, then F is generically smooth. I mean, maybe this is just totally obvious to these people, so they just know this. But F is then generically smooth, which means there's an open set over which the morphism is smooth, actually. So so you get that from there. Okay, good. So that's the idea. So this is a fully fortified lemma, right? There's a lot of stuff in here, and the proof, like we could prove it, like very technically, but the picture, I think it gives the impression, and so I'll just draw this very quickly to remind people / give people who didn't see it last time an idea of how this is proved, right? You take your variety. I'm gonna have to just deal with that. So I'll just make this bigger. I can come back to it if people want me to. So you take your variety, right, and you put it in some extremely large projective space. It's a projective variety, so you can do that if you like. And so there's some massive projective space where this thing lives. Okay. Then you take. So let's think of the variety as being like a surface. If you like, you can do that. And in fact, let me go so far as to make this a divisor. So the divisor in this case will be like a circle on the sphere, if you want. So this is like Z. This is X. Or maybe I should draw it up here. Then you find a sufficiently general subspace of the projective space of a particular dimension. Okay, so this will be Let me actually give the projective space. This is some large projective space. Now you find a projective subspace of a certain dimension. It'll be this size. Okay, so n minus the dimension of x minus 1. Now, in the case that x is a surface and you put the surface in a three-dimensional space, you can check that n minus dimension of x minus 1 would be equal to 3 minus 2 minus 1, which is 0. And then what's the projective space of dimension 0? Well, that's a point, right? And so then we'd be projecting from a point. So that's sort of just like a sanity check to make sure that we're doing the right thing. So let me do this. Okay. So then you start projecting from this subspace by lines. Right. And some of these lines will graze the sphere or graze the surface. There will be some tangents. In fact, there's going to be a whole bad locus of points where this happens. Right? You can imagine that there's some bad locus, which is a circle in this picture, where the lines are tangent to the sphere. And so then you project, and in this way you end up at a projective space that is the same dimension as x. So you end up on some plane in this case. So there's some plane, projective plane. And so this is a projective space of the same dimension as x. They say, oh, but I thought you said you were going to map to a projective space of one less dimension than x. And I say, yes. Right. So far, this is actually just a rational map. Right? This is not a morphism yet, because it's not defined at every point. Right. In particular, it's not defined. Sorry. Oh well, sorry. This is defined at every point. The map from x is defined at every point, but the map from the projective space is not. So I shouldn't say that exactly. But so there's a map now from x. It's a morphism. Sorry, that was confusing. Right, to here. Right. And so let's call that maybe pi, just so that's easier to say. It's the restriction of the projection test. Now, when you do that, you find a point that avoids the image of the divisor. Okay, so this is the divisor when you do the projection. The divisor ends up down here somewhere, the blue guy. And then the branch locus ends up in here as well. That's the red guy. The red guy ends up in here as well. And you take its projection. And then you just pick a point that's not in either the devising, the set of the divisor or the branch locus. Let me give these names too. So branch locus, and then Z is the image of the divisor. The blue guy is the image of the divisor. So pick a point that's not in either of those sets. It's orange, like this guy. This will do. Okay. And then from there, do another projection. So can I do this? So start projecting in the plane. Start projecting from this point now. Okay. And then that will project the projective plane onto a line, which I think I'll just use black again for. And so this might project onto this line, for example. Okay, now that's a projective space of dimension 1 less than x. There's an issue though. It's not a morphism to take x all the way down to that projective space. It's just a rational map. Right? It's not everywhere defined. Why is it not everywhere defined? Well, there's a point, the orange guy, so that over that point, right, there's two cuts in the sphere, or the variety x, where the morphism won't be defined. Right? Oh. Right, the morphism won't be defined at these 2 points, because they're going to get sent down to this orange point, right? And then from there, we don't know where to send them onto the projective line or this p dim x minus 1 because you don't know where to send this guy, right? You know where to send anybody who's not that guy. It's like, oh, I know where to send this thing, right? This thing goes down to here. This is fine. This guy would go down to here, but the orange guy doesn't have anywhere to go. So then what you have to do, getting back to the statement of the lemma, is you have to take a blow up, right? I said that there was going to be some blow up of x. So there's a blow up of x in a finite set. The finite set is in particular those two orange guys. Right? So blow up x at the two orange guys. So I'll write that as I'll just say the orange guys because it's not worth saying. There's just a pre-image of the rational, the point that you projected from under. Well, yeah. Why don't I just write the pre-image of pi? I've already got the notation for it, so let's just do that. So the pre-image of this point, which I'll call p. Right. So that's a modification of x, right, as claimed. It's a morphism, even. And that's what we wanted, right? Yep, so this is the x prime in the theorem, or the lemma statement. And now you say, well, we want to map from that modification onto the projective space. You say, well, that's just fine too, because the blowup actually lives inside of, remember the blowup is by construction inside of the product of x with the projective space of dimension one less than x over a point, over like the spectrum of the field that you're using. And in particular, it's got projection maps, right? There's a projection map onto each factor. And so we'll take the one that projects onto the projective space factor. And so there's a projection onto this factor. Projections are always morphisms. So there's a morphism, right, off of the blowup in particular by factoring through, right? That gets us to the projective space of the appropriate dimension. And then the miracle is that this construction actually gives everything that's in the lemma, right? I mean, of course, we've satisfied part about blowup. The fibers are, why is that true? Well, the way to see that, I think the quick way to see that is, and I was wondering if this was true after I gave the talk last time, and now I realize, oh yeah, it's definitely true. It's even said in de Jong's argument, but I never really noticed what he was saying until like recently. It's funny how that works. Like when you're about to like talk about it, you realize like, oh yeah, that's actually how it works. So there's a really cool argument that's due to Lefschetz, and that gets used all over the place in algebraic geometry, which is that if you have this setup, then you take the point from which you projected down here, and you connect it to the linear subspace from which you projected here. And then that gives a linear subspace. In this case, it's actually literally a line, okay? This is really nice. You make Lefschetz's pencil. That's the reason I'm drawing this a second time, is because I want you guys to see how the curves actually arise. So the curves come from doing the following construction. You connect the two subspaces. You get a linear subspace, which is the axis of what's called the Lefschetz pencil. And so Lefschetz's pencil looks like, I'll do my best with this. So you start sweeping out. That's not a good color. Let me pick, there we go. So you start, imagine like, it's like a spindle. You start spinning out a bunch of planes right around this, this axis. Right? This is the axis of the pencil. Right? And as you do this, right, these planes will cut the surface. In this case, it's a surface, but in general, it would be the variety in curves right? Do this, this. So we have a bunch of curves. So then this one would cut like this, right? So you get all these equatorial circles from this in this particular example. And then in this way, you actually get all the curves. So this is how the family is constructed, which I think is kind of nice. It's very satisfying compared to the abstract argument that you project off of a factor and then argue like, oh yeah, it's got to be that the fibers are curves because the relative dimension is 1. That's like not very satisfying. So this is really what's going on. It's like you're really doing this. And in this way, you get a bunch of circles, right? These are the curves that are in the family. And so now it's very believable, I think, that not only are the fibers curves, but the generic fiber is smooth, right? This is an application of Bertini's theorem now. And because we're working over an algebraically closed field, we don't care about the characteristic in this case, right? So that, I think that gives that rest. That the morphism is finite and it's a cover of the divisor. I think that's clear from the picture also, because right, this guy maps onto here and then that gets projected down. But maybe I'll just kind of ignore that point for a bit. But so this is very nice because now we've turned our variety into a family of curves, and this is a crucial part of the argument that de Jong makes, because now we can start reasoning about our potentially very high dimensional variety as if it's, you know, a bunch of curves, and curves are easy to understand compared to any dimension. So maybe let me pause for a moment and just ask, does anybody have any questions about this this lemma? I know we talked about it last time, but I don't know if people want to ask anything. Okay, so I think it's okay. So we've got a family of curves. Okay, so now we're gonna pick up where we kind of left off last time. So now I'm going to start drawing a different picture of X, because X can now be thought of as a family of curves. So there's a surface. If you want, you can just think of a surface. Throughout, it's going to be fine. There's some surface maybe, and it's fibered by curves. That just means that there's a bunch of curves in the surface. And so there's like this curve. There might be some singular curves. The curves might break up into pieces, right? There's no hypothesis that the curves are irreducible. Okay, so that could happen. But usually, right, like we said, generically, the curves are going to be smooth. So most of the curves are smooth. And then that's a kind of curve fibered over this base, right, which is one less dimension. If you like, you can think of a surface and a line, and that's just fine. Now, I think I'm just going to say this in words for the sake of time, but there might be some concern that the curves are connected, and it turns out that this is not a concern. The curves are in fact connected, and the way to see this is to recognize that if you like, you could take a factorization. If you don't know what this means, just don't worry about it, but if you do know what it means, then it'll maybe help. You can take what's called the Stein factorization of this morphism. And what that does is it just takes curves, the family, and it sort of crushes them. It does like a contraction. So if you have a curve like this, okay, which is broken up into some pieces, then, or sorry, maybe I should say it like this. You've got it. Maybe you say, oh, I don't have a connected fiber. Maybe it looks like this. Okay, well then, what the Stein factorization will do is it'll take the the space above and do a contraction to Z, where Z is a point for each of those connected components. Okay, so there's a morphism from each of these connected components onto a point. So this is a contraction map. That's the idea. So contraction. Okay. And then from the after doing the contraction, you map these say 3 points maybe to 1 point. You just map everything to 1 point afterward, and that's a finite morphism. It's a finite morphism. It turns out that in the construction before, this is actually even étal, which is something that I don't think I can justify right now, but it turns out that that's a finite étal morphism, and so then it ends up that you're actually mapping down to a projective space by some finite étal morphism. And then you cite a fact about the projective space that there are no non-trivial finite étal morphisms to the projective space, which is something that GB and a few other people, George and I have been talking about recently, because pretty much for this reason, actually. Right, so there are no non-trivial finite étal morphisms to a projective space. If you don't believe that immediately, think of the Riemann-Hurwitz theorem, and you can see why that's true, at least for curves. And then it turns out that you can do this inductively. So it actually follows from the Riemann-Hurwitz theorem that this is true, if you know what that is. So I can actually assume that the fibers are connected like this. So this is kind of nice. And so now we've got this family of curves. And now the next thing that we want to do is we want to find a divisor. So let me paraphrase one of the lemmas in here. So there is a divisor in this x prime. Oh, sorry. There's a divisor in this x prime. That is sufficiently twisted so as to cut, let's say it this way, cut each irreducible component of each fiber, right, which is a curve, in at least 3, not counting with multiplicity. So I mean like cardinality 3. At least 3 points in the smooth locus of the fiber. All right. So the picture of this is that you, right, we seek a divisor that is sufficiently twisted, is what I'm saying, so that it snakes through x prime. Right, let me do my best with it. It snakes through x prime. Okay. Cuts each of the curves in the smooth locus. In fact, this has to get through a few more times, right? There we go. Right. It has to get through each curve, in particular, each irreducible component of each curve, at least 3 times, right? And it has to make sure that it never cuts anybody in the non-smooth locus. You got to cut everybody in the non-smooth locus. And somebody says, why is there such a divisor in x prime? And again, this follows from a sort of Bertini-style argument. What you do is you make a pencil of divisors, right? So you make like you might have to first twist x prime a lot, which means like take a Veronese embedding of a very high degree. So like think of like the Veronese embedding of like the like the conics and P5 or something, right? And you can take a sufficiently large degree of the twist so that this linear system eventually has the properties that you need. So if it's okay, I'm not going to get into the technical details of that argument. But what's really going on is that you're doing some dimension counting. Okay, that's really what's going on. So that's the idea. So there is such a divisor. Okay, and let's call that divisor H. Such a divisor. And you can even say more. You can guarantee that H covers the projective space, which is pretty nice. So this map down to here is a finite generically étale map to the projective space. So when you take H down to here, this is finite. That's believable. And generically étale, which is, I guess, that's also fine. Right? It's generically smooth. So these aren't really so crazy, I guess. So it's finite and generically étale. So I'll say also H is, or H2 projective space by the restriction of this map, which I think I called F. And generically étale. So now, at this point, you've got a family of curves. You find this divisor with this nice property. Now what we do is we say, well, after an alteration of the base, let me write this in words. Let me pick something else. So after an alteration of the base, which is the projective space here, the divisor even Z union H, right, can be broken up into sections of the morphism F. Okay, so what do I mean by that? Well, let me zoom in again. So there's this family. I won't draw as many curves this time. I guess I'll just draw this. Right. In fact, let me just do two because too many. So we found this divisor. I should mention that I'm neglecting to draw Z in this picture, but if you like, you can think of Z as being empty, and that's fine. So just think of Z maybe as not being in the picture, and that'll be okay. So let me do something like this again. All right, then this goes through here. It's a little harder. It's easier if this actually breaks up into 3 pieces, right? Anyway, this goes like this, like that, fine, like this. That's fine. I said at least 3, right? So let's just do that. So so that's like, you can think of this as like Z union H. And right now it's not a union of sections, which means that it's not split up into pieces. And so what I mean by that is, what I would like what I would prefer is for the pink guy to break up into pieces. So what I mean by that is I would like actually for this to be the case. The pink thing actually splits up into a bunch of copies of the base space. That would be ideal if I could have this. So I want to get to that, and this will require an alteration of the base. This will require some alteration of the base. So if it's all right, I think at this point what I'm going to do is start just referring to this as x. Okay, it's not literally the thing we started with, right? And then the base I'm just going to start referring to as y, just because it'll be a little easier to work with those things, that notation. And when we do an alteration of the base, so we might come up with some other base space. We can pull back the family of curves along that alteration. So I'm going to try to explain that, and then that will give us a new family with this section, these sections over the base instead. So what we'd like to do is alter the base and then pull back the family along this alteration to make the divisor for Z union H into the union of sections. So how should I? Yeah, I guess I'll do this. So what do I mean by pulling back along an alteration? Well, you see, if you've got x mapping to y, so this is like our original family, and then you do some alteration of the base, right? So you find some morphism to y, say y prime. So this is some alteration. Let's say psi or c. Now remember, I think I actually forgot to say this, but an alteration should always happen from an integral scheme. So this is actually an integral scheme. Sorry, I think I forgot to mention that in the definition today, but I think I said it last time. Now, the reason why that's important is that means that there is a generic point, right? There's a unique generic point. In y prime. And that's going to be important for my construction. Let's call it eta. Then I can take the fiber product of x and y prime over y. Okay, so there's a projection onto here. And then take this map to be the identity on y prime. And take the, inside the fibered product, take the closure of the, I guess this would be the generic fiber inside of the fibered product, which I'm just going to denote by the generic point, if that's okay, right, over y with x. So I take the Zariski closure of this thing inside of here. And this thing is called, the strict transform. Well, this whole thing really, this whole ensemble, right, is called the strict transform of f, which maps from x to y. I write it vertically actually, along the alteration I wrote C down there, but I should write it up there maybe, along the alteration C. So the strict transform of this along the alteration of C. So that's what I mean by pulling back a family. Okay, so like for the sake of having a definition of that, that's what I mean when I say to pull back a family along an alteration. So the claim is that there's some alteration of the base so that you separate the divisor into a union of sections. Now, that just follows from really what is a bunch of algebra. The point is that if you have a divisor and you break it up into its irreducible components. So let me try to write this. So let's just rename Z union H. Just rename it Z because it's just going to be a lot to carry around Z union H. Then break up Z into its irreducible components. Right, so break it up into pieces, Zi. So then that means Z is the union of these Zi's. Right? And then after having done this, remember that Z maps into, Z includes into Y, or sorry, Z includes into X, rather. So that means that, and X maps down to Y. So what that means is that sort of like algebraically, there's a, well, break this up into these pieces. What that means is that algebraically, you can take the function field of X and include it into the function fields of each of these, right, irreducible components. And then from there, the fact that there's a map from X to Y means that there's...
Oh, wait, James, that I don't understand, because Z is much smaller in dimension. How can you go from a big field to that small field? Z will, like for instance, in the picture, X is a surface, Z would be a curve. So you would go from a dimension, transcendence degree 2 to the transcendence degree 1. You can...
Oh yeah, it's not. It wouldn't go this way, right? Wait a second. No, wait. Yeah, sorry. I think I'm not saying this correctly, right? I never seem to. This part never sticks in my head. I have to get a better picture of this part.
I don't think there's any comparison between the function fields here that you can expect.
Yeah, this isn't what I want. This isn't what I want. Sorry. What I want is yeah, take the I think it's the image of the, sorry, 1 second. There's this, then you have a finite separable extension of this. I don't think I want that though. Sorry. Embedded. Oh yeah. Sorry, this is actually what I want. Sorry, I shouldn't be talking about X. I should be talking about Y. So now you get a map actually on the function field from y. That's the mistake. I'm sorry. So ky maps now into each of these, right? Into the function fields of each of the divisors. Sorry, each of the irreducible components, right, like this. That's what I meant to say. Sorry. So you get this map from the function field of ky into each piece, right? Because there's already a map this way, and the dimensions are the same now, right? Because the base, remember, is 1 less than x in dimension. So there are now these maps of fields, and so this is, like I said, this is just some sort of technical algebra statement. Is like, okay, then what I can do is take some large enough. What should I say now? It's like there should be a large enough, yes, a finite separable Galois extension. Okay, so hold on, sorry. Take a finite separable Galois, sort of large enough extension. This is where the alteration sort of shows up first, where the alterations sort of begin happening. So that k of y embeds into this extension. We call this L. Okay, and I also want for yeah, and then I want to know that each of the KZIs can be embedded in L. So I'll say such that KZIs can be embedded into L, I think over, yeah, over KY. That's the idea. So this is really just some field theory statement. It's really not anything that I understand to be entirely geometric. I'd have to think about it more, maybe. I don't have a great picture of this part. But so then once you do this, you say, well then, okay, I've got a finite.
James, can I ask a stupid question?
Yeah, you can ask. Yeah, it's fine.
Can you tell me, I'm sure this is totally dumb, but can you tell me how we know that the extensions, that the embedding of ky in each of the kz's is separable?
Oh, well, I'm just saying, like, just in some separable extension, right?
Well, if these extensions are not separable, then they can't be embedded in a separable extension. So we have to know this is, to get the finite separable extension given them, it's just pure field theory. Just take, you know, because these are finite, they're algebraic because z and y are the same dimensions. So these field embeddings that you wrote down in the right-hand corner of the top page in the thing you have to be finite field extensions. And so there's nothing, the statement that you made at the top of the next page is automatic from basic field theory as long as they are separable extensions.
But we made the assumption that we are generically a tau. And that means that these...
thank you. That's it.
All right.
Thank you, Hans.
Yeah, sure.
Perfect.
Yeah. No, that's great because I don't even know if I'd be so quick to see this, right? Of course, yeah, the point is that, and the reason why I had to say this thing earlier, right, going way back, is that Z actually maps in a generically étal way onto Y, right? So that's like way back. Yeah.
Thank you. That's just what I needed.
Yeah, no, that's great because I don't even think I would have been able to say that as quickly. I probably would have rambled a little bit before seeing that. But yeah, so that's the point. So these guys actually are separable, and then you can make this finite separable Galois extension L, I guess. Yeah. So that's that, I guess. Okay, now, so what's the point? Well, now we've got a finite separable Galois extension L of ky, and so yeah. So now what we do is we say let. So how are we going to make our alteration? Well, we say let y prime be to y be the, so this is the, yeah, so this is the normalization of y in the extension. Well, I should emphasize that it's a finite, right? Finite. Is there anything else? Yeah, finite extension. Field L. So let this be the normalization in this finite extension. So like I'm more used to taking a normalization in the function field of the original variety, but you remember it's like, well, you can actually take normalizations in finite extensions of the variety, and then this is a sort of usual way of getting alterations. So that's the idea. So this is an alteration of y. This is an alteration of y. And pulling back the family of curves, which goes from x to y by f along this alteration, splits the divisor, right? Z union H and X into the union of sections. And we'll call those sections, I think it's probably best to just say it the way that he says it in there, right? So you have a map from X to Y by F, and then there are sections sigma I that go back up. Right? And so the sections should be just thought of as, right, copies of the base space inside of X, like in the picture that's up here. Sorry, I don't know how far I have to go. Not too far. So remember, we wanted to do this, right? We wanted to turn this guy into a bunch of these. And so what we had to do is take an alteration of the base, which amounted to taking some normalization, some finite extension of the function field. And that's why you have to extend the function field at certain parts of the argument. That's at least one reason. There's more, but that's how it starts. So now you say, well, why do you want to do that, right? Like, what's the reason for doing this? You know, why can't I avoid this alteration step? Why do I have to take this alteration? I said, well, the point is that now we've put ourselves into a really nice case. You know, this is the whole point of this construction and why we wanted to go this far. So we've come this far now and have these sections, right, like this, and right. So I need these to cut more. Sorry. So they might even intersect each other. So I want to indicate that too with the picture. So right, the sections might intersect one another. That could happen like this, and others. This could happen like that. And so these are sections of the morphism F. Okay, let me try to indicate that to where I say F. At every stage, I write X, but I'm just updating, right? I'm just updating X to the new total space of the family after pulling back. Right, so throughout this argument, you just keep updating the notation to say X, X, X. You don't write X prime, X double prime, etc. It's just too crazy. So updating X to the new total space of the family and Y, right, to the new base space of the family. Base space of the family. Picture, but now it's a little bit nicer. And in particular, we have these sections. Right, so here's a section, here's another section, here's a section. Right, so we get all these sections now, etc. So these are the sigma i's. Okay. So this is a very nice case. And you say why? I say the reason why this is nice is now look what we've done. we've done something really cool. We've now marked these curves in some points, right? So we've marked these curves in some points. And it turns out that the way that we've constructed this family of curves is so that the genus is constant in the family. So the genus G of any curve in the family is constant. So it's a bunch of curves of the same genus. And it's also true that we've marked the curves in a sufficient number of points in some sense, right? We marked the curves in n greater than or equal to 3 points in the smooth locus, right? And so now we just have to be a little bit careful because, it might be that, who knows, maybe maybe you have a fiber that hits one of these sections like this in like a sort of bad place, so that the sections intersect. So it's like, okay, well, if you have a fiber like that, then just cut it out of the base, right? Just take that point and just excise it from the base, right? So if you take this that's not a good color. Take this point, right? This point has a bad fiber in some sense. The sections come together over this point. So you know what? Just take this guy out, right? Excise this. And this guy's got a bad fiber. It's got a singular fiber. So just get rid of that too, right? And then in this way, you start cutting out, right, the singular fibers and things like this. And what's left after having done this is an open set. Okay. So then when you do this, then you end up with an open set in the base, right, away from these bad points. And so now what you've got is a family of curves that are smooth, of genus G with n marked points over an open set. So in this way, we acquire a family of stable curves of genus G with n marked points over an open set of Y. Right. So now if we restrict our family to this open set, we've got a family of curves. So let's call that open set U. Okay. Now I say, okay, great. So we've got this nice family of curves now. And you say, why is it stable? And you say, well, this is some definition due to Deline and Mumford when they were trying to prove things about the moduli space of curves. They came up with this notion of stability. And one way to think of what stability means is just with this equational criterion that says that you need for 2 times the genus minus 2 plus n to be positive. So that means that you have stability for the curves. Sorry, this has to be for each irreducible component. Sorry, for each irreducible component. but we've got that, right? That's what that whole thing was about, with getting this divisor that was sufficiently twisted and all of this stuff. Because when you're reading this, it's like, why do you want to do that? And then like later on, you say, oh, I see why you wanted to do that, because now you've cut the curves in a sufficient number of places to argue that they're stable, right? So now you've got a bunch of stable curves. So this is a really crucial part of the argument. It's really, really crazy, actually, that this gets used in an argument about resolving singularities. And you can actually get a solution of singularities if the characteristic is 0, which is kind of cool. That's stated in the abstract. If you're curious, you can just ask me about it. You can find it on the internet, though, too. But so now, let me give the idea of how this proceeds. So you've got a map now from U, well, from XU, which is the restriction right over this open set. So this is a family of stable curves of genus G with n marked points. So now we say, well, a family of curves, stable curves of genus G with n marked points, is as good as a map into the moduli space of curves. So this is where we start using the moduli space to our advantage. It's like a leveraging that we can make now. So if you have a family, that means that you have a map. At this point, I'm sort of crossing into the territory of stacks, but don't worry about it, because it doesn't really matter, actually, for what I'm about to say. So like, if you're worried like, oh, that's a stack, that's not a scheme, it's like, oh, don't worry about it. It's a space. It's just some space, and it's fine. Because everything I'm about to do doesn't really depend very much on the fact that they're stacks or anything like this. It doesn't really matter, so don't worry about it. So you get a map into the moduli space, and now there's a claim. The family that we have can be made into a family of stable curves. Well, at this point, I think I have to say semi-stable curves over an alteration of the base y. So just briefly, currently the family of curves that we have over y is not a family of stable curves. We can't say anything about that family. These curves could be really bad, right? They could have cuspidal singularities and things like this, or they could break up into pieces and things. So we don't know that the family can be made stable over y. That's not clear. The claim is that after performing an alteration of y, we can pull back the family, which currently exists, right, which is stable over u. We can even pull it back to this alteration, and over the entire alteration, of the entire altered base rather, you'll have this family of stable curves. And stable curves are very nice because their singularities are only as bad as like nodal crossings like this, right? So what we're going to do is alter the base so that the family becomes a family of very nice curves, which are easier to understand in terms of resolving singularities. That's the whole idea. I know we're technically out of time. I guess what I'd like to do maybe though, if I have a moment, is just like give the idea of how you go from this map, right? You've got this morphism, right? How do you turn that into an alteration of y, right? So I think I can do that in like 5 minutes. So if people can wait like 5 minutes, I can give an idea of how that happens.
Sure, and then what is also and how is that then? That you can also tell us then how this is then the resolution.
Yeah. So at first it's not a resolution, right? At first it's not a resolution, but after I do all this stuff and I get this alteration of y, I pull back, I potentially get an alteration of x. I've got some alteration of x. Then because it's an alteration, you can actually make the function field has been extended by a finite amount. It's a finite extension. At that point, you have to do a little bit of arguing and massaging, but you can make the alteration what's called Galois. And so you can make it so that there's a finite group acting on the total space. Then if you take a quotient by the action of that finite group, you've got a quotient singularity. Now that's a modification of x. Right? You've got x and the quotient mapping onto x. That's a modification now. So now we've gotten rid of the alteration. The alteration is gone after taking that quotient. And then all you have to do, quote, all you have to do is resolve that quotient singularity. Right? Once you've gotten that far, you just resolve the quotient singularity. If the characteristic is 0, it's clear how to do this. It's a well-known thing. That's what Abramovich and de Young's paper is about. If the characteristic is not 0, you'd better hope that the characteristic doesn't divide the order of the group that's acting on the variety. That is the only case. That's the only case that we don't understand, right, as a community, is the case where the group is divisible by the order of the group is divisible by the characteristic. So it's very interesting because this arguing the only problem that we have, right, as a community in resolving singularities is quotient singularities by groups, singularities that arise by quotients of groups whose order is divisible by the characteristic, which are called, what they call the wild quotient singularities.
Sorry, yeah, but that's actually not what I wanted to ask. I want to ask is, how does it now solve the original theorem? Where is the non-singular model? In all these things, I'm looking for a non-singular smooth model to pop up. And where is it? After alteration. I don't want to do resolution. That's not what I meant.
How am I going to get the yeah, I understand. So even with the alteration, let me just maybe say this in words. I'll do my best to say it in words. So you get this alteration, and this alteration is not yet smooth. That's what you're saying. You're saying it's not yet smooth. It still has these stable curves in the fibers, which could be singular. So then you have to then what happens? I didn't prepare this part so much because this is a little technical, but I think people who are better at resolving singularities than me can understand this part maybe more quickly than me. But like the point is that because the fibers have at worst nodal singularities, there is a structure to them that you can write down equationally. You can actually write down the equations defining the singularities in the total space. They're very explicit. It's like x times y minus the product of a bunch of t's, t1, t2, t3, etc. So they become very explicit singularities. In fact, they're toric, I think, right? Because every toric variety is defined by like binomials or something like this. So it's defined by binomials. So they're toric singularities. So they're very explicit. And then at that point, you can just do blowups and wash them away. That's the idea. But that's a little vague. If you want to talk more about it afterward, we could do that. Or yeah. So that's the idea. Is that the singularities become very explicit at that stage. That's the point. Okay. So very briefly, I'll try to give the idea of how to construct this alteration of y and thus of x. If that's okay. So so you've got u mapping into the moduli space. Okay. At this point, yeah, there's stuff going on with stacks and things, but let's just not worry about it so much. Now, there's a finite étale. I'm just citing theory now. So if it doesn't make a lot of sense, it's okay. I don't really understand it either, but I can at least say the words and get the point across, I think. So there's a finite étale morphism, technically of stacks, but it's not going to matter too much. This is what people call, this is the moduli space equipped with what's called a level L structure. So there's some level L structure which sort of rigidifies the curves so that they don't have automorphisms in some sense. I think that's the idea. But anyway, it's some stack, and this turns out to even be a representable morphism. And what that means for us, all that we have to know about what it means is that I can take a fiber product of stacks like this, and in doing this, rest assured that, so I'll say this, the representability hypothesis implies that this is a scheme. So we're back into the back in scheme land, actually, after taking that one fiber product because of the representability hypothesis. So at that point, you can just rest assured, oh, okay, everything's a scheme again, I'm okay. And now you say, well, how is that going to get me an alteration of Y? Well, now let me just box this thing off and give it. Let me just start writing this with a box because I don't want to have to write this every time. It's just too much. This might break up into irreducible components. So in principle, you'd have to take some irreducible component. But for now, if it's okay, I'm just going to assume that it's irreducible, because if not, then I would just take an irreducible component and do the same argument. So let's just assume it's irreducible for the sake of discussion. And then, so then what I do is I take the closure. I'll talk about the irreducible component, I guess. Let's call this thing C. There's a map by this C into the fiber product. Okay. And I take the closure of the image of that map inside of the closure of this space. Taking the closure, by the way, is how I introduce the nodal singularities in the total space. Okay, I'm sorry, this is a little quick, but like I want to get the idea across, and at least so that people can see. So I take the closure view, that's Y again, right? And now from there, I've got this map from this thing into here, and now I've got a projection onto Y, right? It's a projection onto Y because the fibered product has projections. Those are always morphisms. So that's the point, is I'm taking the closure of the graph in some sense inside of the fibered product, and then I'm projecting off of one of the factors. That's always a morphism. It's just like the blow up from earlier. That's why I said this argument comes up very often, actually. And so I get this map onto Y, and this is the alteration of Y, actually, that I want. This is an alteration of Y. You say, why is it an alteration, not a modification? You say, well, that has to do with the fact that the map above was a finite étale morphism. It's finite. That's going to cause this to have potentially, right? Oh, sorry, I didn't mean to do that. That's going to cause this to have generically finite, maybe not one-to-one fibers. And that's kind of the reason why is from this. Yeah. So then after you do that, you have an alteration. I'm getting to the end of this now, I promise. So you have Y, X, right, over like this. Now there's this alteration. So the closure of this thing has an alteration like this, the projection onto Y. Now you can take the fibered product, right, over Y with this closure of the image of this thing. That's going to be, or wait, have I think I might have taken too many steps.
You have to take the stick transform, not the fiber product.
Yeah, I'm sorry. I think I made I think I'm trying to go too quickly. I think I'm going to make a mistake. Hold on. I can. Let me just. I wrote this down. in advance because I was worried about this part. Yep. Okay. So there's a map from, yes, okay. So now, yes, I forgot. We need to use the other projection. So we have another projection off of this thing, right? We've got a projection to y, but also a projection onto here. So now what we want to do is take, yeah, so now we want to take the closure of the image and instead project onto, right, instead we want to project onto this guy. And then we have to, this is why I knew something was wrong. You have to use another fact about the moduli space, that there's a universal family over this moduli space with L-level structure. This is like just some crazy fact about moduli spaces that I really don't totally understand, but there is some universal family that lives over this space. And the point is that because there's this universal family, as there is in, like, you know, in the typical geometric scenarios, if you have a universal family, then all families, right, have to pull back from that universal family. So you can pull back along the universal family and get a new family like this. And we're almost to the alteration. You say, well, what's the alteration? So this is a new family, right, over the base. Or sorry, a new family, right? New family. And now this family exists over an alteration of y. So this family universal space, sorry, exists over an alteration of y. That alteration is given by projecting onto the other factor, which is y. You can project off of the fiber product in the other way. And now the problem is that, yes, I have a map from X down to here, but I don't know that this is a morphism. I only know that this is a dotted map. This is only a birational map. The point being that these two are actually isomorphic on an open set, but I don't know that that isomorphism comes from a morphism. So this is some other technical issue that has to be done, you know, sort of dealt with. And if I don't even know how to explain that right now. It's a little bit much for me. But there is a way to deal with this that has to do with the fact that they're stable, and you can actually guarantee that this is a morphism. So it's not clear immediately, I agree, but this turns out to be a morphism. All right. Okay. This turns out to be a morphism. Now you've got a morphism, so you can take the strict transform, or sorry, you can take the family now to be over this altered base by pulling back. Yeah, by pulling back the family along the alteration. Yeah, I think that's the idea, right? I want the something like this. Now I'm getting a little foggy on what to do at this point, trying to do it quickly, but then you get to a point where you have a scenario consisting of, I'm just gonna update everything, so I'm gonna rename everything. So you've got X and Y. You're back to like having X and Y again. You've got X and Y. Y is some alteration of the original Y. And what you do is you use the inductive hypothesis now. So use the inductive hypothesis to alter Y by a regular variety. So now this is some regular variety. This is some alteration where I'm using the induction hypothesis at this stage. And now this gets to the thing that I tried to say out loud earlier, Hans, that you can pull back along this, right? Take the strict transform, right? Sorry, I have to take the strict transform of this, which means I have to take the generic, so the generic guy up here, take a closure. And I get a new family. And then the claim is that that family has very explicit singularities. That total space has very explicit singularities due to the stability of the fibers that we acquired through going to through the moduli space. That's the sort of point. So I'll just write that sentence. So this new family has very explicit equationally singularities and can be resolved by blowups that are fairly explicit. So I think at that point I'm gonna call it quits. But it's
yeah, that gives a good idea of what is going on. Yeah, I didn't. Okay, thanks. That's actually clarifies quite a lot for me now, because I've heard him talk about this 20 years ago, and at that time I was not ready to follow what he was saying, but now I understand how it works. Yeah.
Well, yeah, I'm glad that this gives an idea. You know, like I didn't plan to get into the technical details in complete incomplete generality. It's insane. I mean, there's a lot of stuff going on, but yeah, I mean, you see the idea though, right? It's like the idea is, you get a family of curves by doing some classical algebraic geometry in some sense, and then that family can be made a family of stable curves, but you have to go through the moduli space. You have to sort of, wade through that. And then when you finally get that, you can use the inductive hypothesis. Yeah, that's the idea. So.
Well, thank you very much, James. We're a bit over time, but okay, I guess we can.
You, James.
That's okay.
I guess, we don't have commuting time. Right?
I was just thinking the same thing. Yeah, we can.
You guys don't have to go, right? So.
Yeah. We're already there.
Who knows when we will ever be, in person again, right?
Yeah.
By the way, Ben, I wanted to say I'm sorry I haven't answered your email, but I will answer your email probably soon. Okay. Yeah.
No problem. I would never expect a fast response from any academic on anything, especially if there's substance involved.
Okay.
It's good to set the expectation, right, Ben?
Okay. All right, guys. So we're gonna have our next talk is gonna be Mio. Is Mio still there?
Yeah. He's there waving at us.
I don't see everybody. Oh, okay, I should do this. Okay, yes. So I need the abstract, I think, still from you, right? Your mic is off. Your mic is off.
Yes, sorry about that. Yeah, I somehow thought I sent it. I think I was sending several abstracts, and I think
but please send it again, because I somehow didn't seem to find it. Okay.
Yeah. No, I will. Yes, and Laura was actually also mentioning the same thing this morning. When she...
Yeah. Okay.
So what is happening? That the Graduate Center sends out a bulletin on Mondays announcing the talks for the next 2 weeks. So it's nice if the web page is updated, so people also, outside our group, but will read the bulletin, know what's going on.
Yes. No, of course, I'll send it. I just for some reason, I thought I'd send it, but I think it was, I realized it was probably a different, different abstract I sent to a different group.
Send us like what it is that you were planning to talk about to see if it was appropriate for the seminar. But
Yeah.
Yeah,
I'll
right.
make
That's
it
right.
into,
Yeah, you read the description rather than the sentence. Yeah, that's right. Right. Yeah. Yeah.
yes, I'll make it into more of an abstract, appropriate for
Okay.
yes.
So that people will actually have more chance to read it, right? If it's
Yes,
up.
yes.
Okay, guys. So thank you very much for all attending, and thanks, James, for a very clear, nice pictures. I like your pictures.
James, you must have learned a lot going through this because, you know, is also so much background and so broad. So